After 15 years of doing advanced process control projects, I always recommend MPC. Model Predictive Control's ability to optimize multivariable systems with constraints is hard to match, but it's easy to get wrong. I know I have. So here are 5 lessons to save you time and trouble. Lesson 1. Imagine you're starting to race professionally, but you only have your old car. So you take it to the workshop and tune the engine, transmission, weight balance to have acceleration and curve taking. And then you go to the racetrack and lose to everyone by a mile because you didn't actually practice and learn the circuit. That's what it's like to have PID compete against MPC. The lesson is MPC is not just a fancy PID. It's something completely different because, like a clueless driver, PID only reacts to what's immediately ahead, while MPC actually knows how fast to take one curve so that the other one can be taken better. Both controllers can only take one step at a time. Here you see PID behavior. But MPC is calculating an optimal solution based on a number of steps that it can take. It's also correcting after each step based on the deviation from reality. And that's the thing. If you're going to compare something that can plan and correct versus something that can only correct, planning and correcting are going to make a huge difference. In the topic of planning for the future, autonomous operations are not something that happens by chance. You need to design the structure to support it. Request a meeting to discuss your path to autonomous operations with us in the link below. Lesson 2. Have you ever been to a blind person's house? Here's a piece of advice. Never move their furniture around. Why? Because they have memorized the whole space and furniture position in their mind. Just like a blind person moves around their house based on the model in their head, MPC will control your plant based on the model it has of it. It's not really looking into the future. Nobody can. It's just running a simulation to predict future states and optimize the control actions. If your model is bad, MPC will struggle. The lesson is models matter. At first, I underestimated this only to get slapped in the face by unstable operations and excessive control action, because the predictions do not come from the past actions alone. They depend on the model of your plant. That said, you don't need a perfect model, just one complex enough to capture the dynamics you care to control. Maybe a first-order transfer function is good enough for your heat exchanger, so start with that, and refine it later if you need to capture more new ones. Lesson 3. Controlling one output that only depends on one input is not very complex, but if you add another input or 2 more outputs, it gets messy. Picture this. You're driving down the road on a sunny day, sun hitting you on the side of the car, on the passenger side. And that poor passenger wants to cool down. But the thing is, you are kind of cold yourself, so you want to turn the heat up. Fortunately, you are driving one of these fancy cars with independent temperature control, but it's not going to be so easy. The controller actually needs to consider the set point of the other side to be able to harmonize and get to each of the set points individually, because it's not about 2 individual controls trying to reach individual set points. They're actually mixing with each other. And that's what MIMO is. You have multiple inputs, 2 fans, and multiple outputs, the temperature of each individual person. And they are interacting with each other because the cool air from the passenger side is cooling down the driver who's cold, so the hot air from the driver's side is also messing up with the passenger's temperature. The lesson is MISO or MIMO are a necessary evil sometimes. In real industrial applications, we see this all the time where you need to control multiple inputs to get your desired output or outputs. Consider, for example, a hydrocyclone circuit in mining, where to get your output, which is your particle size distribution, you actually need to control the flow, the pressure, and the density of the incoming material. Another great example is a cement kiln or a furnace in a steel mill. Kiln or furnace temperature are maintained by controlling the fuel flow to the burners, while the complete combustion of the fuel is done by controlling the mix of air and fuel, so the airflow coming in, basically. More fuel increases the temperature, but more fuel also needs more air, and the incoming air cools down the kiln or the furnace due to the dilution effect. On the other hand, unused oxygen means you're losing energy in the stack. Optimizing fuel flow and combustion airflow together is a common MPC application. And yes, it's true. You can avoid the complexity of MIMO by using some clever tricks, special math, scenario grouping of your controlled systems. But what you're doing is essentially just shifting the complexity around. And often, you're making things worse. If the process is multivariable, the controller should be too. Lesson 4. Remember the blind person from earlier? In industry, there's a thing called a bump test. It consists of sending homeowners to walk around their house bumping into things to know where they are. Just kidding. But it's a similarly painful procedure where you need to disturb your plant by a known quantity of input and then observe what the change in the output is reacting to that change in input. That allows to create a model, which is very necessary for model predictive control. Yeah, just try to imagine how complex that would be with a MIMO system. It is very complex. Okay, most tools require a bump test to identify the process, but bump tests aren't always feasible, and they can disrupt your production schedule. Customers hate them, operators hate them, nobody really wants them. Still, MPC can't be made operational without a good enough model of the plant. The lesson is model identification is critical. Critical and hard, and if you don't do it, you don't get to run MPC on your controls. There was this one time when I had to run a kind of complex bump test in a flotation circuit which had 7 tanks in a row. And I was there with the operator. We had all the safety procedures in place. So we had these safe valve movements. We were trying to identify the level to valve dynamic. 1%, no change. 2%, no change. Because they weren't changing, we decided to move to larger steps of valve movement. 3%. 4%, 5%. And then we get a call from the field operator. Pulp is flowing from places it shouldn't be. We look at the security cameras and effectively we have basically ruined the process stability. The operator takes control, manually fixes everything, starts... Obviously, they don't allow me to continue the tests. I later found out that the level sensors were actually stuck and they were never going to let us know anything about the dynamic of the process. So I had to go back to my spreadsheet and actually interpolate or make some educated guesses as to what was the actual dynamic for those cells. And honestly, that's a very typical experience in model identification. Things just don't go your way. Lesson 5. No model stays perfect forever, and that's completely normal. The plant changes. Evolves over time. Equipment wears, instrumentation drifts, operating conditions shift. This might affect how your MPC performs, but it doesn't mean the system is broken. It means it just needs a little bit of care. In many cases, small changes or periodic updates are good enough to keep things running. And it's very rare that you need a complete overhaul, because just enough change to keep things aligned with the real process is good enough. There was this one plant I worked with where they had a spare pump that didn't meet the original specs. We had an MPC there, of course, and at some point after the implementation, they swapped the pumps. And after that, the MPC was really struggling to do a good job. It was so bad, actually, that we were called to action and had to turn off the system to have a good look. During this inspection, we realized that the difference between the pumps was too much for the MPC to actually be able to do a good job. So we had to keep the system off while we identified a new model for the spare pump. After some time, we had the model and we added some logic that would swap the model together with the pump. And that worked. I later revisited some other systems that also had spare pumps, and they were good because the pump was similar enough. I mean, a spare pump is never identical. They do wear over time, and when you swap them, yeah, the controller can deal with some difference. There's, of course, a breaking point where this no longer applies. And if you have completely different equipments, that might be the case. Anyway, the lesson here is model error is expected, and it's something you can deal with. With the right tools and mindset, you can live with the error and keep your MPC effective without constant overhauls. Here's where I wish I had SharpBot years ago. You see, in traditional MPC, the model lives inside the controller, but in SharpBot, it's outside and it's completely independent. Look at this example. This is a wood and berry distillation column model. Based on the equations available, we have the simulation of this plant. The simulated plant is controlled by an MPC. The MPC is actually looking at the models, not at the same models that are running the plant right now, but it has a replica of those models. And in the controller definition, here are the models. You see here we have G11M, which is this guy. G11M is giving us the response for G11, basically. And we're using these models for the transfer matrix of the plant, and we also have 2 extra models for the feed forward. And right now, the set point is not reachable, so MPC is just trying its best to stay as close as possible. But what if the plant is actually a bit different, a lot different? Then it's really easy to just update that on your model of the plant. And what will happen eventually, and that's about what was happening with the spare pump. It was too much. But if you update the model, then you can get to a steady state. Look at that. And it got there. So there you go. You saw that it's really easy to change the model on the fly. If the change is too much, I would recommend to stop, change it, and then switch it back on. But even then, I did get it stable after some time. So with SharpBot, the models are independent and outside, and it's really easy to tweak them. You can actually change them, and you can be using different blocks for the models. Here we're using first-order transfer functions, but you can use higher-order transfer functions, and you can even use other blocks. You can even use C# code. Whatever works as a model of your plant will work as a model for your MPC. Automation Inc. is all about autonomous operations, and MPC is a big part of that. If you found these lessons useful and you want to learn more about how we can set up MPC in your operations, click the link in the description and request a meeting with us. So that's what I wish I knew before implementing MPC. It's powerful, predictive, and flexible, but it comes with challenges. The good news, you don't have to face those challenges alone. With tools like SharpBot, you can stay ahead of the curve and keep your plant running smoothly. Thanks for watching, and if you want to learn more about process identification for autonomous operations, go check this video.